So the first thing we're going to do today is have you pull your green periodic table out of its sleeve. By playing with these little pieces from the ion charge puzzle, we've actually figured out that there is a pattern to what kind of ions they make. So above the first column, I want you to put in a 1 plus, and above the second column, I want you to put in a 2 plus. That kind of goes with the idea that all the 1 positives ended up in the first column, all the 2 positives ended up in the second column. And then we're just going to keep going using only the tall columns. 3 plus. You didn't have any examples of the 4, but they actually can go positive or negative. So we're going to put 4 plus or minus, and then count it back down. 3 negative, 2 negative, 1 negative. And you also didn't have any examples of the noble gases because they don't make chemical compounds. And the whole idea of the ion charge puzzle was built on the idea of looking at compounds to figure out what kind of charge things had. So now we have a real simple system. If you need to know the charge on the ion, it's going to go 1, 2, 3, 4, 3, 2, 1, none. Based on where it is in the periodic table, we can predict its charge. The transition metals are kind of an annoying group. They have positive charges, but their charges are going to be variable. So above the transition metals, we're just going to write positive but variable charges. And that will help us remember that because they're metals, they're positive. But the weird thing about transition metals is that we can't predict their charge based upon where they are in the periodic table. Now, you won't get this periodic table on your tests and quizzes, but I will allow you to take a dry erase marker and write onto your test periodic table because they're in a shiny sheet. You can write these numbers onto your periodic table when you take a test, but you are going to have to know that it goes 1, 2, 3, 4, 3, 2, 1, none. So I figure at this point we don't even need the ion squares anymore because we now have a way to predict the charges on things in such a way that we have all the ones that we just did plus more. So you can scoop up your ion squares and you can either keep them if you want to be able to play chemistry go fish with your friends, or you can take them and you can deposit them into the recycle bin because we have a better, quicker way to get the job done now. And then we're going to kind of look back at last class. We did a lot of different things last class, but I want to look at what are the things we need to take forward from there. Like what were the big gains? So for those of you who like to ultimately have some notes to go with your chemistry world, these will be the things that will constitute some notes to go with your chemistry world here. From our last class, we played with a light bulb. We looked at things that lit up the light bulb and things that didn't. And then we used some blue solution, and we made some chlorine gas, and we made some copper, and then we drew some pictures of ions. We came up with some new models. We learned about, basically with those new models, how to draw pictures of things that were in their normal state, and today we got to turn that into dissolved state. So some big conclusions from last class. Deionized water does not conduct electricity. You've been pretty much told your entire life to keep electricity and water separate from one another, and somehow underlying that is the assumption that water conducts electricity. Turns out water is actually a horrible conductor of electricity. At least deionized water is a horrible conductor of electricity. Deionized water is the ultimate in clean water. It has nothing else in it. Tap water has all sorts of things in it, like fluoride ions, because they put them in there to try to help keep your teeth nice and strong, and chlorine, because they clean up the water so it doesn't have bacteria. And here in Neenah, you have lots of magnesium and calcium because we have a relatively alkaline soil, so we end up with a lot of hard water and mineral deposits in our water. So regular water has lots and lots of things in it, but deionized water is water that has all that stuff taken out. People always want to know where I get the deionized water. Right now, I'm just buying it at the grocery store. We do have the ability to make it. We're waiting on the hoses to come in to go with our deionizer. Our deionizer is basically a giant Brita filter. The filter itself is about 18 inches tall and maybe 4 inches across. So it's like the biggest Brita filter you can imagine. And we just hook it straight up to the water lines. We run tap water through it. There's stuff in there that grabs each and every one of the ions found in tap water. So by the time our hoses come in, we will just make the deionized water right here and on site. Thought number 2, some substances dissolve in water to allow the water to conduct. Others don't help the water conduct. So we found out when we dissolved stuff in water, they either lit up the light bulb or they didn't light up the light bulb. The things that allowed the water to conduct were things that had both a metal and a nonmetal. And the things that did not allow the water to conduct consisted of only nonmetals. So we came up with a way that we could look at the chemical formula. Based on the chemical formula, we could then make a prediction about whether it was going to help the water conduct electricity or not help the water conduct electricity. And then we played with a dish of copper chloride, and the goal was to try to figure out which ions were positive and which ions were negative. We figured out that the chlorine ion is negative because it was attracted to the positive pencil lead, and the copper ion is positive because it was attracted to the negative pencil lead. We knew from elementary science that opposites attract one another. We used the battery to make one pencil lead positive, one pencil lead negative. And now we knew that the chlorine ion was negative and the copper ion was positive. Then we took that one step further and we worked on our ion charge puzzle. Knowing that chlorine was a -1 and having a big list of chemical formulas that the different elements were able to make, from the ion charge puzzle we could start to infer the charge on different types of ions. And then this morning we learned that the charge depends on a column in the periodic table. So we put in the numbers, and from this point going forward, if we need to know the charge on an ion, we're just going to look at our periodic table, and we're going to pull the ionic charge straight from there. We also talked about what it takes to conduct, that the ability to conduct electricity requires two things. The first thing that was required was charged particles had to be present. In the case of a wire, those charged particles were electrons. In the case of the solutions, the only other option was we had to have ions present. Since the copper chloride could conduct electricity, we inferred then that the copper chloride was made from ions. And in our electrolysis of copper chloride activity, we actually drew this little model for copper chloride in its solid state. That its chemical formula was CuCl2. It consisted of 2 chloride ions and 1 copper ion. You counted the electrons in each one to give it the appropriate charge based upon the number of protons that were there. And then this big box around the outside indicates that that's still in the solid state. We also kind of looked at the idea that the 2 chlorine ions wouldn't be right next to one another. They're both negatives. Negatives don't like negatives. So when we assemble compounds like this, we have to put them together in a positive, negative, positive, negative, positive, negative, alternating fashion, because if you try to put the 2 chlorines right next to one another, they're just going to push apart because they're both negative. So in its solid state, the copper chloride looked like that. And we kind of picked up this new model to show protons and electrons without having to draw all of the particles, or all the subatomic particles. The other thing that was required to conduct electricity is that the charged particles have to be free to move. Fix that. Dissolving basically is going to have to free the ions from one another. So knowing that it's made of ions and that it doesn't conduct like this, where the charged particles aren't free to move, but it does conduct when it's dissolved in water, the inference here is that dissolving it breaks whatever's holding the positives and negatives together. We know that when it's dissolved, the positives and negatives can move around separately from one another because all the negatives went one way when we hooked it up to a battery, and all the positives went the other way when we hooked it up to the battery. So we know that they had to separate from one another, which means that if we wanted to think about the dissolved copper chloride, this might be an okay way to think about it. It's the same pieces, but they're separated. And we don't even need to be so fancy in our model here. We can go with just a real simple, here's the chloride ions. And so the copper ions and the chloride ions separate from one another, and that's what it means to take a compound made of ions and dissolve it, is to break the connection between the positives and the negatives and allow all the ions to move around separately from one another. Now we've met the two requirements to be able to conduct the electric current and make the light bulb light up. We've met the requirement of having charged particles present if we infer that the compound is made of ions, and by allowing the water to separate those, we also have a model that allows the charged particles to be free to move, and we can account for the conducting of electricity. So at this point, I want you to get your dissolving compounds in water sheet back out again. So we have a whole bunch of data on the front here about things that conduct and things that don't. We need to work toward getting the pictures filled in on the back of this thing. So after looking at things that conduct electricity in water and things that don't conduct electricity in water, and looking at the metals and the nonmetals, we basically came to the conclusion here that anything that had both types of element present, both metals and nonmetals, was going to be able to conduct electricity in water, and anything that only had one type wasn't. And I actually, at this point, am going to have you take copper off the list, simply because it's not a compound. We're going to limit our discussion here to compounds. So we're going to just take the copper off the list. I wanted it there because it avoids a misconception from developing, but we really want to focus our attention on the compounds. One of the things we need to do today is we need to rename these things. We can't just go around calling these guys type 1 compounds. They need a name. We just figured out that copper chloride is made of ions, and so everything else that's in that same category of being able to conduct electricity must consist of ions as well. Type 1 compounds are called ionic compounds. They get their name because they're made of ions. And from an element type standpoint, they contain both metals and nonmetals. Our type 2 compounds are going to need a name as well. We'll name them in a little bit, but these are the compounds that contain only nonmetals. Now, obviously, it's about to become extremely critical that you can very easily make the distinction between metals and nonmetals by looking on your periodic table. For now, you're probably somewhat dependent upon your little colored periodic table. Over the next few days, we are going to do metals and nonmetals so frequently that you actually will, I think, learn to do this without your little colored periodic table. But the first step in really everything we're going to do for the next couple of weeks is start with the question, what type of elements are in your chemical compound? And you're going to go from there. So now we're going to take this idea of the ionic compound and try to draw a picture to represent what's going on here. So our copper chloride did conduct. Yes, at least it did when it was dissolved in water. And then I had to pick one of the type 2 compounds. I picked the littlest of the type 2 compounds because we're going to have to draw some particle level pictures, and I wanted to pick the one that was going to be the easiest to draw. I picked the isopropyl alcohol. No, it didn't conduct electricity when it was dissolved in water. In its pure form, we've already determined that the copper chloride consisted of a copper 2 positive ion, and on either side of that, we had a negative chlorine ion. And we'll do that just to represent that it was a solid. So that picture we already had. This other one is a little more difficult to draw. In general, when you have carbon compounds, the carbon atoms tend to be in a line. So we're going to take the 3 carbons and we're just going to stick them in a line. In this particular case, the oxygen is sticking up and off the middle carbon. And then the 8 hydrogens are just going to go kind of all around the rest of this stuff. There's 1, 2, 3, 4, 5, 6, 7, and 8. At this point in your chemistry career, I don't really expect you to be able to get the structure right on these. Anything you came up with that had 3 carbon atoms, 1 oxygen atom, and 8 hydrogen atoms will be a perfectly acceptable structure. But since I was drawing it for you, I decided to put it together the way that it actually looks. So in their pure form, this is what these compounds look like. We'll tackle first the copper chloride in the dissolved state. So copper chloride dissolving in water, we knew we had charged particles. They were free to move. If you're an artistic type and you want to draw a light bulb inside of here and show light beams coming off of it, you're certainly welcome to add a light bulb. And we're going to give ourselves a shorthand. We are going to have lots and lots and lots of things we have to draw in here that are dissolved in water. And dissolving water molecules, or drawing all those water molecules is going to get to be kind of a nuisance when they are in fact not all that critical to the actual atom counting thing. So we're going to use this little abbreviation of a tiny little v to represent a water molecule. Water molecules are bent. You built them with the model kit when we did the stuff about our atmosphere and about greenhouse gases, and you found out that water molecules have kind of a V shape. So our shorthand for something full of water there you go. Quick and easy, we have a beaker full of water. And we've managed to determine that when the copper chloride dissolves, it falls apart into copper ions that have a 2 positive charge and chloride ions that have a 1 negative charge. And I'm going to dissolve a second particle to make our beaker look a little more full. So there's a copper 2 positive, and every copper 2 positive has some Cl negatives to go with it. And now we need to understand the difference between my light bulb and a battery. Because the coppers and the chlorides are just kind of scattered randomly throughout the beaker. And yet, last time we were in class, I had you do something where you hooked up power and you sorted out the coppers and the chlorides from one another based on being positive and negative. Here is the difference between a battery and a plug. A battery is what's called direct current. The battery has a positive side, it has a negative side, and the side that's positive is always positive and the side that's negative is always negative. So when you hooked the wires up to the battery, you were able to create a pencil lead that was positive and a pencil lead that was negative, and then you could make the ions sort themselves. The light bulb is different. The light bulb plugs into the wall. Our electricity is what's called alternating current. Alternating current flips its direction. I believe in the United States it's twice every second. So when you look at the prongs on the light bulb, they're positive and negative, and then half a second later they flip the other direction, and then they flip back, and then they flip the other direction, and back and forth and back and forth and back and forth and back and forth. So one prong of the light bulb never stays positive long enough for the negative ions to get there. By the time they head that direction, the prong becomes negative. That's the meaning of alternating current. So when we draw the picture with the light bulb in it, these prongs are alternating between positive and negative 120 times every minute, which basically means that the ions don't ever sort themselves out. Based on that, the conditions are simply changing too often. There are a lot of things in the world that we need to plug in that require direct current. Your Chromebook is one of them, as are most electronic devices. The solution to that is the black box thing that's in the middle of your Chromebook charger. That black box is called a transformer. The transformer box takes alternating current and turns it into direct current and allows your Chromebook to run. Even though it likes direct current, your Chromebook can run on being plugged into the wall as long as you have a transformer box. Anything that you plug in that has a really big plug or has some kind of a box thing somewhere between where you plug it into the wall and where you plug it into your device is a device that runs on direct current. You know your Chromebook runs on direct current because it runs on battery. We just have to transform our alternating current into direct current if you want to run the Chromebook plugged into the wall. And then if we wanted to write a chemical formula for this situation, we would write CuCl2 AQ, where AQ stands for aqueous, which means dissolved in water. Now, this isn't actually the first time we've seen this. We had kind of a preview of this happening back when we did the chemical and physical changes lab, when we had the picture of the water and the salt, and then the salt dissolved in the water. We see kind of the same situation. Here's the water molecules. Notice their cute little V shape. Here's our alternating collection of positive, negative, positive, negative, positive, negative. And then when we put the two together, the positives and the negatives came apart from one another, the water got in between them, and they ended up all scrambled up. So we've actually seen this before, but we're finally far enough along to kind of understand a little bit about what happens. So that's your ionic compounds. When they dissolve in water, they fall apart into ions. Because those ions are free from one another and can move around, they can carry an electric current. Ionic compounds cause the light bulb to light up, and the lit up light bulb is our evidence for the presence of the charged particles in the solution. Now we have to deal with the isopropyl alcohol. I'm going to pose two possibilities here. We know a little bit about the isopropyl alcohol. We know that it doesn't light up the light bulb, which tells us that either we don't have any charged particles at all, or that if we do have charged particles, the process of dissolving doesn't free them up and they're not able to move around. So I figure there's a couple ways we could draw this. Possibility number one would be to go with kind of the same theme we went with the ionic compounds, except assume that it falls apart into atoms instead of falling apart into ions. Possibility number two is that the molecules of isopropyl alcohol actually just distribute them in and amongst the particles of water. And I think we can actually use our noses to answer the question of what is true about this. I let you sniff the isopropyl alcohol, and it smelled really, really strongly like rubbing alcohol. Your noses and your tongue are extremely dependent upon molecular structure. Things smell the way they smell because of their molecular shape. Things taste the way they taste because of their molecular shape. So the fact that you were able to take pure isopropyl alcohol and identify it as a water and isopropyl alcohol mixture tells us that the molecule inside the rubbing alcohol solution that you have at home, which is isopropyl alcohol dissolved in water, must contain molecules that are structurally identical to the 100% isopropyl alcohol. The very fact that you could make that identification tells us that this isn't true. If idea one were true, the rubbing alcohol wouldn't smell the same as the isopropyl alcohol. Not only that, if idea 1 were true, we'd probably see some bubbling when we dissolved it, because the hydrogens would buddy up and the oxygens would buddy up. They'd make diatomic pairs and they'd go away as gases, so we'd see some bubbling and fizzing upon dissolving. We didn't see that. We didn't see any conduction of electric current, and we did observe that both things smelled like rubbing alcohol. So idea 2 is what all the evidence says is likely to be the case. So take a moment and draw idea 2 into that second beaker. You could probably get away with like 2 molecules of isopropyl alcohol if you're not feeling like you really want to try to squeeze 4 into that little container. I have a big advantage. I can digitally draw 1 molecule, and then I can do duplicate, 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 and make lots more real easy. Your pen doesn't do that for you. And then we can label this C3H8O aqueous to say that it's been dissolved in water. And with this, we can now go back and we can give the type 2 compounds a name. Type 2 compounds, when they dissolve, stay as molecules. And so our type 2 compounds, we go all the way back here, we are going to name them molecular compounds to represent the fact that they dissolve into molecules. So we now have ionic compounds that are formed of metals and nonmetals. Because they're made of ions, they conduct electricity when they're dissolved in water. We have molecular compounds that consist of only nonmetals. When you put them in water, they just separate into individual molecules that mix in with the individual molecules of water. And because they don't have any charged particles, the molecular compounds aren't going to conduct electricity. Now we're going to kind of take the molecular compounds and we're going to set them aside for the day. And the rest of our day, we're going to spend focusing on the ionic compounds.